Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Mr. Kadim Khan and I am a lecturer in the Institute of Computing, Quart University of Science and Technology. Today we will take lecture number 19 of the subject of Introduction to Computing, in which we are going to discuss the number systems conversion. And in this lectures we will take the binary number system to be converted to decimal number systems, to the octal number systems, and to the hexadecimal number systems. And here we will provide you different computational examples of each one. While in the previous lectures we already explained different types of number system, including binary number system, decimal number system, octal number system, and the hexadecimal number systems. This is the discussion agenda. First of all, we will explain what is the binary number systems. Then we will explain the applications of the usage of binary number systems. Then we have the conversion of binary to the decimal number systems with the help of two different examples. Then we have conversion of the binary to the octal number systems, which has the base 8. Also we will explain examples of the conversion of binary to the octal number systems, and at the end we have the conversion of binary to the hexadecimal number systems. Here we will also provide you different examples of the conversion of binary to the hexadecimal number systems. First of all, what is a binary number system? As its name indicates, the binary number system is a system which has two important digits, and the digits are 0 and 1. So they have the base 2. According to the digital electronics and the mathematics, the system is in fact consists of the numbers that is expressed in the binary systems and having the base 2 as a numeral systems. So it means that there will be two different digits in the binary number systems, and the digits are 1 and 0. So the base 2 systems is in fact the positional rotations with the 2 as a radix hairs. Now the binary number systems is applied internally by the computers, and in fact it is applied by the computer to perform certain operation by the arithmetical and logical units of the central processing units. And almost all latest computers use the binary number system to directly convert the instruction to the certain sorts of the commands. So binary number system is used by the electronic circuits using the logic gates. So the logic gates are in fact implemented by the assembly language programmers to develop the certain system which works on the on or off of concerns. In that sometimes we requires to on the machinery and sometimes we requires to off the machinery. Every digit is referred here as a bits here. So binary number systems, each and every digit is called the bits, and bits is the minimum storage capability of the computer. Now where the binary number system is used, and what are the common uses of the binary number systems? The binary number systems are commonly used in the computer applications, and these applications are mostly well developed by the assembly language and the C++ language, and also some other high-level language like Java, etc. So all the codes or the functions are used by the C++ and the Java languages. The binary number system utilizes these functions. The binary number systems have two digits, as we expressed earlier, that is 0 and 1. So these digits are used to write programs or encode any digital data. So the computer understands only the coded language here, and the coded language is expressed in terms of the binary codes here. Therefore, we have just two digits which express each and every commands used by the computer systems. And these informations are stored by the central processing units, and then these information are processed by using different commands. And these commands are also expressed through certain binary digits, either 0 or 1. This is the tables which will give you the complete idea about the binary number systems. 0 means nothing. So when certain digits that starts with the 0, so it means that nothing. And 1 means 1 unit, so it means that 1 instances, then we will express it as a 1. But 1 0 here doesn't mean tens, it means 2 in the binary number system. And 1 1 doesn't mean allowance, it means that 3. And similarly 100, which is 100 actually in the decimal number system, but it actually is 4. And similarly 101 is 5, 110 is in fact 6, and so on. So these are different binary number representations. So here you can see that this is 100, which starts back at 0 again, and then we add 1 to the number on the left here from this side. But the number is already at 1, so also goes back to 0, and 1 is added to the next position, to the left position of this number. Similarly here you can see that it starts with 0, and again for all 3 digits 1 is added to the left here, and so on. So means that when this number is incremented, so here we will add 1 here, and when that 1 is incremented, it will be converted to 1 0. So this is the incrementation of the binary number systems into the computer concepts. Now first we will convert the binary number to the decimal number systems. You know that the decimal number system is that system which has the base 10. So for examples 1, 2, 3, 4, 5, 6, 7, 8 and 9, these are used to represent the decimal number system, including 0 as well. So from 0 to 9, all the numbers will be expressed in terms of the decimal numbers. This is the first example which will enable you to understand the conversion of binary number system to the decimal number system. So this example converts the binary number 11001010 into the decimal numbers. And there is no binary point here, no fractional part as well. So we will convert that into the binary numbers, into the decimal numbers. Remember that you cannot read it like that one. For example, if it is 1010, you cannot read that 1010. It is 1010. Now, here are 7 positions, which is the most significant bit, and this is the 0th position, which is the least significant bit. Now, you must have to count all these bits initially. So, for example, this is 0th position, 1, 2, 3, 4, 5, 6, 7. Overall, these are 8 bits, but the most significant bits position is the 7, starting from this 0. So 0th is the first position, then 1, 2, 3, 4, 5, 6, and the 7th position. Now how we will convert that binary number to the decimal number system? First you need to write the full binary number system with the base 2. And you need to write it into the braces or into the brackets. These are the small brackets with the base 2. Then as you here you can see that the most significant bit is at the number 7. So 1 multiplied with 2 raised to the power 7. Then this 1 multiplied with 2 raised to the power 6. Then this is the 0. 0 multiplied with 2 raised to the power 5. And this is the next 0. So 0 multiplied by 2 raised to the power 4. And this is 1 multiplied by 2 raised to the power 3. This is 0 multiplied by 2 raised to the power 2. And this is 1 multiplied by 2 raised to the power 1. And 0 multiplied with 2 raised to the power 0. So you can see that here we have multiplied each and every bits here at the number of which is the binary numbers, each and every binary number here with its base, and the base is power with the most significant bits, and it is decrementing. So for example 7, 6, 5, 4, 3, 2, 1 and last one, which is the least significant bit, it is the 0. Now then we will calculate each and every multiplications with their powers. So 2 raised to the power 7 is 128 and multiplied with 1 is 128. Similarly 2 raised to the power 6 is 64 because 2 2s are 4 2s are 8 2s are 16 2s are 32 2s are 64 and then multiply with 1 is 64. Obviously anything multiplied with 0 is equal to 0, so this is the 0 and similarly this is also 0. And this is 2 raised to the power 3, 2 2s are 4, 2s are 8, multiply with 1, it is 8. Similarly, this one will become 0, this one becomes just 2, and this is also become 0. When you sum all these values, so you will get 202. So you should write the base 10 with 202 and you should enclose this number in the brackets. This is the small brackets with the base 10. So this is the required um, decimal number and we have converted this binary number into the decimal number system. And this is quite easy concept here. This is another example, but this example is a little bit different from the previous one because here we have the fraction part, which is that point here. So we are going to convert 1010.1011 into the decimal number. And there is the binary point here with the fraction part. So we will use the same techniques, but here the most significant bit and least significant bit's position is little bit different. First, we have written here 1010 point, that is the dot 1011. It is the binary point or the fractional point. Here is the most significant bits in this part of the binary number. Its position is 3 because starting from here 0, 1, 2, 3, you must have to start the 0th position of the first value. So 0, 1, 2, 3. So its position is third. That is 3, third position. And here is the binary point. Now also you need to define here. This is minus 1th position. If it is the 0th position, this one will be the minus 1th position. And this is minus 2th position, minus 3rd position, minus 4th position. So this bits have minus 4th position, which is the least significant. This one is the most significant, having 3rd position, and this is minus 4th position in the least significant bits, while this one has the 0th position and this one has the minus 1th position. Now how we will convert that binary numbers to the decimal number? First we will write that particular binary numbers here with the brackets. This is the small brackets and having the base 2. Then we will multiply each and every bits to its base, and also we will write the power over the base. And the power over the base is in fact counted from the most significant towards the least significant. So 1 multiplied by 2 raised to the power 3, which is the third position of 1. 0 multiplied by 2 raised to the power 2 for this, plus 1 multiplied by 2 raised to the power 1 for this, and similarly 0 multiplied by 2 raised to the power 0. Now this part of the expression before the fraction point is in fact defined here with the 0 multiplied by 2 raised to the power 0. Next is the plus 1 multiplied by 2 raised to the power minus 1 plus 0 multiplied by 2 raised to the power minus 2. Similarly 1 multiplied by 2 raised to the power minus 3 and 1 multiplied by 2 raised to the power minus 4. Now the easy concept is there that before this point, this fraction point, here it is the fractional point, you have to provide the power of n minus 1, that where n defines the number of bits in this binary number. While here you have to define the power with the completely n, but you have to start with minus 1, minus 2, minus 3, minus 4. Here you have to start 0, 1, 2, 3. So here you can see that we have provided the powers of the base with the minus, that is the negative powers, minus 4, minus 3, minus 2, minus 1, then 0, 1, 2, 3. Now 2 raised to the power 3 is equal to 8, and obviously anything multiplied with 0 is equal to 0. So this is the 0. Similarly 1 multiplied by 2 raised to the power 1 is equal to 2. this is obviously 0. This is 1 multiplied by 2 raised to the power minus 1. So this is 1 over 2, which is equal to 0.5. So 2 power minus 1 is 1 over 2. This is 1 over 2 raised to the power minus 2 is 1 over 4. So anything multiplied with 0, it will become 0. So this is 1 multiplied by 2 raised to the power minus 3. 2 raised to the power minus 3 is equal to 1 over 8. And 1 over 8 is equal to 0.125. This is 1 over 16. And 1 over 16 is equal to 0.0625. When we calculate all these expressions, the sum will be 10.6875 to the base 10. So this is the conversion of binary number to the decimal number here. The next conversion is the binary to the octal number. You understand that the octal number is that number which have the base 8. First, you need to convert here 101011 to the given decimal number and then decimal number to the octal number. So here is the examples of converting the binary to the octal number, and the number is 10101001 base 2. So given number is 10101001 base 2. First we convert given binary to the decimal number. For this purpose we will use the previous methods. So we will multiply each and every bit pairs with to the base of the binary number, which is 2, and also we will provide the powers for each and every base. So it should be n minus 1. Here you can see that 1, 2, 3, 4, 5, 6, 7. There are 7 bits in this. So starting from 7 minus 1, it is which is 6. So 1 multiplied by 2 to the power 6 plus 1 0 multiplied by 2 to the power 5 plus similarly 1 multiplied by 2 to the power 4 plus 0 multiplied by 2 to the power 3. Similarly 1 multiplied by 2 to the power 2. Then we have 0 multiplied by 2 to the power 1, and finally we have 1 multiplied by 2 to the power 0. Now when we calculate all these expressions, so 2 to the power 6 multiplied with 1 is 64. Here it is 0. This is 2 to the power 4, which is equal to 16. This is 2 to the power 3 multiplied with 0. So anything multiplied with 0 will give us 0. 1 multiplied by 2 to the power 2 will yield 4. Similarly, this will give us 0. This will give us 1. 2 to the power 0 is equal to 1. So 1 multiplied by 1 is equal to 1. When we compute this, so overall it will become 85. 64 plus 21 is equal to 85. But 85 is not in octal, it is in the decimal. To convert that into octal, we have to use this technique. So start divide 85 by 8. So 85 tenths and 5 is the remainders here. Then 10 should be divided with by the 8. So 1 is 8. So 2 is the remainder. Similarly, 1 cannot be, in fact, we cannot divide 1 by 8. So we will just write here 0, 1. Because here you can see that when this number becomes less than that the divisor here, which is 8, so you will write this number as a remainder and you will write 0. So you need to multiply 8 with 0. So when you multiply 8 with 0, so answer is 0 and 1 is the remainder. So 0, 1, 2, 5. Now 0, 1, 2, 5 will be the required octal numbers of this binary number. So 0, 1, 2, 5 is the required octal number here. Here is the another example for your practice. This is 01101 2. Now this is our binary numbers. To convert that into octal number, first we require to convert this into the decimal number. So 0 multiplied by 2 to the power 4, because there are 5 digits, so we will start from 4 plus 1 multiplied by 2 to the power 3 plus 1 multiplied by 2 to the power 3 plus 0 multiplied by 2 to the power 1, which is obviously we will not write the power here of 1 plus 1 multiplied by 2 to the power 0 So then we will calculate all these expressions. So 0 multiplied 2 to the power 4 is equal to 0, 1 multiplied 2 to the power 3 is equal to 8. Similarly, 1 multiplied 2 to the power 3 is equal to 4, and this is 0, and this is, in fact, 1 multiplied 2 to the power 0, 1 multiplied 1 is 1. Now, when we compute this expression, that is 8 plus 4, 12, 12 plus 1, 13, it is the decimal number. Now, start divide 13 by 8, because 13 is the decimal number. We will convert that into octal. So, when we divide 13 by 8, so remainder will be 5. And when you can see that 1 cannot be divided with the 8 completely. So, that's why we will write here 0 and this 1 here. So the required number is 015, which is just for, in fact, 15. So here for the equivalent octal number is 15. You can also write 0 here, but 0 is not in fact required here. So that's why just 15. Now here you can see this is the 0. You can also eliminate this 0 because this 0 will not affect the answers. So this 0 will be eliminated. So you will start your number from these positions. Now this was the conversion of binary to the octal. Now we will convert the binary to the hexadecimal now. So there is the examples of the binary to the hexadecimal numbers. So you know that in the hexadecimal systems we have the base 16. So there are 16 different numbers in the hexadecimal. For example, in the hexadecimal we have 0, 1, 2, 3, 4, 5, 6, 7, and then we have 8, 9. After 9, there will be no 10, 11, 12. There will be A, B, C, D, E, F. F stands for the 15, which is equal to the 15 of the decimal. Similarly, E will be equivalent to the 14, and D will be equivalent to 13, and C will be equal to 12, and B will be equivalent to the 11 here. Now, you should have this table into your minds. Binary numbers are not required here. For example, you should know about the decimal numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But after 9, there will be A, B, C, D, E, F here. So this is the examples with us. Let us convert this binary number, which is 10001101, having the base 2, into the hexadecimal format here. First, we need to group this number with the 4 binary bits because we are converting it into the hexadecimal. So that's why we will make 4 different groups of the bits here. But how we will start different grouping? We will start from the left to right position. So this from the in fact right to left position. This is the rightmost bit. This is the leftmost bit here. So we will consider first these 4 bits, then another 4 bits. If there are less number of the bits at the end position than the 4, we will introduce 1 0 more to the last bit. So we will group every 4 binary bits from the right to left, and finally then we will combine the results here. So there is the examples 10001101 to the base 2. So here you can see that first we have created 2 different groups 1011 here 1011 and then 001 0001. So these are 2 different groups we have formed, and first number, which is 100, in the table of the binary, here you can see that we will search this number in this table. Here it is the 1000, which is equivalent to the 8 in the hexa. So we have written here 8. Similarly, 1101, we will search this number into this tables. So here 1101, it is equal to the D. This is equal to the D, and this is in fact 13 in the decimals, and 13 in the decimal is equal to the D here. Similarly, 1000 is equal to the 8 in the decimal, and there you can see that also it is equal to the 8 in hexa. But 1101 is equal to 13 and 13 is equivalent to the D. Now we will write the corresponding hexadecimal number to each group here. These were two different groups, 1000 and 1101. So here we will write 8 and this will be the D. So 8D to the base 16 is the required hexadecimal number. So here we have converted this binary number to the equivalent hexadecimal number with the help of grouping here. This is another depiction of the binary to the hexadecimals conversions. You can see that this is the number 100 and 1101. So we have divided this whole number, this is in fact the binary number, into two different groups of 8 bits. So starting grouping from this position 1011 and then goes towards 0010. Now in the table 1000 is equivalent to 8 in the hexa, while 1101 is equal to D in the hexa column. So we have written here 8 and D, which is 8D. So this is in fact the conversion of the binary to the hexadecimal numbers. Here we have another different examples to convert the binary to the hexadecimal. So this is the number which we are going to convert into the hexadecimal numbers. First we will write down the binary numbers, then we will group this binary numbers here. So we will group these numbers starting from the least significant going towards the most significant, and the groups will be of the 4 bits. So group all the digits in the set of 4 starting from the least significant bits far right, and then if there is in fact less numbers than the 4s, for example in the groups we have some less numbers, so we will introduce 0 to the leftmost positions here. So we will introduce 0 to the left of the last significance bits if there aren't any enough digits to make a set of 4s. So but here in this case we have 4 bits in the group, so 1010 and 1011. Now use the tables which we have provided here. So for example 1011 in the table 1011 is equal to B. So this is equal to B. Similarly 1010 is equal to A here. It is equal to A. So use the table for conversion of these bits to the hexadecimals. So we have converted each set of the 4 bits into the hexadecimal. So this is the BA. So BA is the required hexadecimal equivalence to this binary number here. So this is another representation of converting the binary to the hexadecimal number. Now I suggest to you that you should also find out some other examples for the converting of binary numbers to the other number systems. So as we have discussed different examples in our lecture here, you should do a thorough practice for converting the one number system to another number systems. In the upcoming lectures, we are going to take another number system for conversion. For example, how we will convert the decimals to the binary and decimals to the octal and decimals to the hexadecimal number systems. So you should find out more relevant examples of converting from binary to the other number systems, so that you will get good practice and you should be able to solve any sort of the question in the exam papers. Now dear students, this is the end of the lectures. Here is the book reference for you. The book is in fact very useful books, and it is the binary, octal and hexadecimal number for programming and computer science, and it is written by the Sunil Tana. So you should download and read this book, and it is very quite close to the programming concepts, and also it will enable you to how these number systems are used in the architecture of the computer systems. Also, if you have any questions, you can ask this question through the email. My email is m.kadim@kust.edu.pk. I will wait for your question and will respond soon as you send me your emails. Also, you can post your queries through the KCMS. I will answer your queries and will receive them. So you can also ask questions about any other topics of computer science, and the discussion is not just limited to the topics of the lectures. You can ask any questions through the email or through the WhatsApp or through the QCMS. So I'm very much grateful for you if you send the questions so that we will discuss these questions for the concepts of computer science. Thank you very much.